Good afternoon and welcome everyone in the Fields for Thought session. In this session, we discuss important topics relevant for research in theoretical high energy physics and gravity. Today, we have among us Dr. Debangshu Mukherjee. He is a postdoc at POSTECH and APCTP in South Korea. He did his PhD from Chennai Mathematical Institute in India on fluid gravity correspondence. Following that, he did various postdocs in reputed institutes in India and abroad. His research has touched upon several topics, including matrix model, conformal supergravity, black space holography, RG flow for holographic field theories, black hole thermodynamics. Over to you, Devanshu.
Thank you, Arpita. So first, let me start by thanking Arpita and Dr. Kumar Abhinav for giving me this opportunity to present some snippets of this really vast subject. So as we decided while I was talking with Arpita, that so this is going to be a series of talks on this particular topic, and this is a topic that I have been working on for the last 7 years or so. Now, in general, this topic, as I also mentioned in my abstract, is quite vast and it has varied kind of applications. But I will primarily focus on a particular kind of application, which is matrix model applied to problems in that arise in high energy theory, primarily in the field of gauge theory. And also I will connect it to models of low dimensional gravity as we go along. But for the beginning aspects, things will be quite general. So with these comments, also please, since this is going to be a series, and there is honestly no dearth of time for us. Please feel free to stop me at any point of time if you want me to repeat something, if you have any questions, because there is no hurry to finish anything by any particular deadline. So if I don't finish something, I can always push it to the next session and plan accordingly. Okay, so let me start by motivating why exactly one wants to do a matrix model. So one of the most intriguing questions happens to be currently, and for a while now, within theoretical physics, is exactly what is the quantum theory of space-time. Now, over recent time, there has been a dramatic shift in the understanding of what and how space-time will emerge. Rather, it is now widely believed that classical space-time, as we see it within our theory of general relativity, is in some sense emergent. It's sort of like a collection of microscopic degrees of freedom, which strongly interact and give rise to some sort of effective interaction, which we feel as gravity. So this is in fact reminiscent of, such kind of emergent collective phenomena is actually something which we are kind of trained to do within our study of physics. In fact, we had been doing it all the way since our studies in statistical mechanics, where we typically have a box of gas where the constituent particles have primarily more microscopic laws. The laws are more chaotic, they're more ergodic, but somehow when we do averaging, what emerges is a collective phenomena, which typically have much more simpler dynamics compared to the ones that make up the complicated large size system. Now, the thing is that even for, by the way, for generic spacetimes, how gravity emerges is largely unknown, and some aspects of how exactly gravity and quantum mechanics can be put together has been done in the context of ADS spacetime, and this is precisely what is known as the ADS CFT correspondence. But in general, things are still not known. So this is actually a very concrete motivation to study matrix models and understand exactly how, given a large number of degrees of freedom, how these constituent degrees of freedom interact and sort of gives rise to a theory of gravity. Now, a very natural setting of packaging large number of degrees of freedom are within a bunch of matrices or higher rank tensors or vectors. So in this sense, vector models, matrix models, and tensor models are a very natural structure to study field theories, which will have certain symmetries, but at the same time, they will have also very large number of degrees of freedom. So precisely, this is the purpose of this series of discussions that I'm going to do over the next few weeks or so. So our focus will be primarily towards matrix model. So our degrees of freedom will be arranged in roughly n cross n matrices, and we will see how exactly one works with such objects. Now, the history of matrix model is actually quite rich, both from the perspective of mathematics as well as from physics. In fact, the first application of random matrix theory in physics dates back to 1956 from the first works of Eugene Wigner. And what Wigner did was he tried to understand energy level spacings for the spectra of heavy nuclei, such as uranium 238, which is one of the isotopes of uranium. And so energy level spacing effectively means the difference in energy, the difference between two consecutive energy levels. Of course, so there are certain details that I am not explicitly mentioning. So you have to sort of normalize these energy levels so that the mean density of these energy levels still stays one. And once you normalize it the correct way, you will see that they follow a certain kind of distribution. So what Wigner asked was, he asked this question that instead of trying to solve this highly complicated Schrodinger equation that is followed by the nuclei of this heavy atoms, what if the Hamiltonian is so complex that it can be treated itself like a random matrix? And what is the distribution of the spacing between these neighboring energy levels? And Wigner's proposal was, sorry, is my cursor visible? Hello?
No.
Uh, okay, I'm unable to get it to work. Okay, anyway, let me still go ahead. So Wigner's proposal was basically that if you start with a system, or rather an ensemble, which is made up of real symmetric matrices where the entries are drawn from a Gaussian ensemble, and if you simply try to calculate the energy eigenvalues of such a ensemble, then it turns out that they very nicely, or rather quite approximately nicely capture this particular energy level spacing. Now, one must notice that this is actually a huge conceptual leap. Before this, typically when people used to work with theories, you would write down a theory and you would have a particular ensemble where, in case of microcanonical, you would keep your both energy and charges and your masses constant. For canonical, you would lift off the condition that your energy is fixed, and for grand canonical, you would keep your chemical potential fixed. But effectively, at the end of the day, there were a bunch of states which followed certain conserved charge, and you would average over this bunch of state. What Wigner came and said is that, there is this particular system that I want to study, and a good approximation would not be a single theory, but a bunch of theories. So when you change and you select random Hamiltonians, you're not simply going from different states in an ensemble. You are literally changing, you are literally like changing, going from one theory to another. And in some sense, averaging of all these theories is what will give rise to interesting physics. Now, Wigner surmised that this, and it's called a surmise because when Wigner first came up with it in mid 1950s, 1956 to be precise, the level spacing of random n cross n real symmetric matrices drawn from a Gaussian distribution looks something like this. And this formula is very interesting. So he firstly gave the asymptotic form of the formula. So this is a formula which is kind of true at large n, when you have when the size of these matrices are very large. So yeah, we will come to discuss about what exactly does this function p of s mean. So as I was saying, so this was pretty much a guesswork that Wigner did. Of course, he later backed it up with concrete calculations, although quite simplistic. The central takeaway from this formula is the following. So S kind of is a measure of the difference between eigenenergies of two consecutive states. Like it's EI plus one minus EI, where EI being the eigenenergies of the ith state. The central takeaway is, if you notice, when these two eigenvalues are very close, the probability actually decreases very fast. Or in other words, the probability of sampling two eigenvalues very close to each other itself is very small. In a sense, each eigenvalue kind of feels the presence of a nearby eigenvalue and tries to avoid it. So this phenomena has a name. It's called level repulsion. But at the same point of time, they don't repel each other so much that they go very far away, because there is an exponential factor which you see, e to the power minus pi s square by 4, which kind of again tries to brings them together. So because when s becomes very large, also this exponentially damping factor is going to make the probability very low. So there is this sort of repulsion attraction business that goes on, which gives rise to interesting physics. Now, subsequently, after these developments in the 1950s, Thuft in 1974 actually found a very profound connection between matrix model and quantum gravity. And what he realized was that in the large n limit, there are these particular field theories where the degrees of freedom are matrices. And there is this very nice way of writing these theories of matrices as sum over surfaces. And these kind of sums started resembling string theory amplitudes. So this kind of suggests that there are some very specific matrix model which can kind of serve as an alternate definition of string theory. And by the way, low energy limit of these string theories are precisely gravity. So in a sense, this gives us a novel understanding and a novel window into how to tackle problems in quantum gravity. And this is precisely what will be our focus today. Then in the 1980s, things like this, ideas of random matrix theory was also applied to quantum chaos. Of course, quantum mechanically defining a notion of chaos is very difficult. So as is well known, classically, the way chaos is defined is you start with two initial conditions which are very close to each other, and somehow when you wait for a significantly long amount of time, you see that the trajectories of the particles involved, they become widely separated. Now, quantum mechanically, it's not at all easy to generalize this notion. Firstly, because in quantum mechanics, you don't have a notion of a trajectory. You have something very fundamental like the Heisenberg uncertainty principle, which does not allow you to have concrete trajectories. So how exactly are you going to define the notion of chaos, and so on and so forth? So towards this, BGS, I mean, Bohigas, Giannani, and Schmidt actually conjectured something, and their central conjecture is that they also observe things like level spacing, which is that the difference between two consecutive eigenenergies of a typical quantum system. And their conjecture effectively says that if these follow random matrix-like behavior, the system is quantum mechanically chaotic. So this is something that has been under intense investigation over the last few years, and there are extremely interesting models like SYK model. There are all sorts of vector models and tensor models where people have been studying these conjecture. Until now, of course, not many, no violations of this has been found. Matrix model also was applied quite massively through a diverse fields of physics and mathematics, actually. So it was applied to number theory, it was applied to spin glasses, then understanding the large and limit of gauge theories, which is what is called large and collective field theory, which was developed in the 1980s by Javicky and Sakita. And this is something that I would like to focus on in the next couple of lectures or so. And also the next thing, which is lattice gauge theory, where novel third order phase transitions were discovered by Gross, Witten, and Wadia. Wadia independently from Gross and Witten. And this is precisely what is known as the Gross-Witten-Wadia transition. It was applied to knot theory, and even more recently by Mariam Mirzakhani to understand Riemann surfaces, something extremely interesting called Weil-Peterson volume, which are basically moduli space volumes. And post 2005, this has been also applied to understand financial markets, how stocks work, and also very recently, in 2017, it was also applied in the context of neural network and machine learning. So overall, what I want to sort of convey to you is the central message that matrix model has a wide range of application, and but more or less we will be mostly restricting ourselves to understand strongly coupled large and gauge theories, more particularly the large and limit. So this is more or less a rough outline of what I would like to cover. Uh, so how does one do quantum mechanics or field theory with matrix valued field? What happens when the size of these matrices are very large? So this second question and kind of the first question partly will be answered today. Uh, what is this approximate resulting effective theory at large? And so you have given me a theory of matrix model. Like, how do I explicitly work with it? How do I take the large limit? How does one even analyze once you get the effective large in theory? If you write down a continuum field theory, how do you understand their dynamics, thermodynamics, phase transition? Because I just mentioned that some kind of novel phase transition does turn up, like third order phase transitions, which is known as Gross-Witten-Wadi. How do you exactly analyze phase transitions for more generic matrix models and so on? And then the last two questions, which of course are again something which is a very active area of current research, which is that how do these well-known matrix models relate to other known theory? And turns out that they are very intimately connected to gravity, in particular what is known as JT gravity. So again, JT gravity, I mean, since the work of Stanford and Marla Sena has been since 2015 or so, has been a very interesting avenue to understand. And of course, a very central question to all of this is exactly what can one learn from the matrix model side about these theories of gravity? Okay, having explained more or less my plan, let me now actually start with the actual material. So what we at the end want to do is we would like to look at some kind of quantum theory where my degrees of freedom are matrices. Now, before we jump into that, conventionally, field theories are defined via an action. So you have a function and you have some kind of Lagrangian, which is dependent on field and its derivative. Here, D is the number of dimension, and M is the manifold on which the theory lives. And you effectively define an integral like this. Now, what you do in typical classical dynamics is you take this Lagrangian, you extremize it via a Lagrange equation, and you try to solve these equations. And that kind of gives you what is known as the saddle point dynamics or the classical dynamics of your theory. When you want to look at quantum aspects, you have to go beyond this. And of course, there is a very well-known prescription due to Richard Feynman, which is that you define something called a path integral. So when you try to have try to get into quantum aspects, you define a functional integral like this, which I have called Z here, which is nothing but the partition function, which is an integral over all possible configurations of this field. So what this essentially means is now it does not necessarily mean that your field can only take up saddle point configuration, but can also go beyond that. And that's precisely what the quantum nature of path integral means. Now, instead of working with something very complicated, let us first focus on something simple. So at the end of the day, what we would like to have is we would like to integrate certain kind of field configurations. Now, this partition function, the path integral, which I just defined, it contains information of correlators. If you take functional derivatives of this object, it is going to give you correlators. You have observables, you have response functions, all sorts of things can be derived from it. Now, what you can do is you can imagine working in an extremely simplistic setting where this action is a simple polynomial of phi. In particular, you can imagine that it's your space-time dimension, which I was denoting here with D. There are no space-time dimension, but rather S of phi is just a polynomial. There are no integrals. And so there is this thing that I have mentioned that S of m is some kind of gauge invariant polynomial. I'm going to explain what exactly I mean by gauge invariant. Just imagine, but for the time being, let us assume that S of m for the time being is some kind of polynomial which depends on n cross n matrices Mij. For the time being, I am not specifying anything about the matrices. They can be anything. Now, a very simple example for what kind of action you can have is given here. So S of m can be half trace m square. So of course, if you write down m in terms of its eigenvalues, if the metric is if the matrix is nice, non-degenerate, and stuff like that, then of course this and if all the eigenvalues are positive definite, then this object Z that you see will be well behaved, it will be convergent. And you can also even write something more complicated where you introduce higher order terms, which you would call interaction, which is there in the second line, which are terms that are proportional, that are sitting with some coefficients GP. Uh, Now, what we want is, of course, working with a general matrix, but ideally that is not possible. Working with all possible matrices M in such an ensemble actually does not even make much sense. So what one can do is one can try to specify ensembles, try to put on more and more symmetric structures to M, such that the models that are under consideration become somewhat tractable. Now, depending on the symmetry class of the system, what one can show, and this is something, it's a theorem that follows from mathematics. What one can prove is that there can be only three possible class of Gaussian ensemble at least. What does that mean? By that means if your leading piece in this S of M is quadratic, which is what would make it Gaussian, then you can have only three possible categories of matrix model. One is Gaussian orthogonal ensemble. That is, your matrices has to be real and symmetric. Gaussian unitary ensemble. That is, your matrices has to be made up of complex Hermitian matrices. And Gaussian symplectic ensemble, where your matrices have to be quaternary self-dual matrices. So your entries will be quaternions. So, by the way, one thing I would like to point out, you see the nomenclature here, Gaussian orthogonal ensemble, does not mean that things are made up of orthogonal matrices only. They can be real symmetric matrices. Similarly, GUE means Gaussian unitary ensemble. It does not mean that the ensemble is made up of unitary matrices. It is made up of Hermitian matrices. These nomenclatures are nomenclatures which diagonalizes this corresponding matrix. So you give me a bunch of Hermitian matrices, but what I can do is I can act on it with some unitary matrix. So I have a Hermitian matrix M. I can do some operation like U dagger MU. This is going to diagonalize those matrices. And that is what is the nomenclature named follows. So it's the matrices that diagonalizes the corresponding ensemble elements. That's how they are named. So these three ensembles arise from Dyson's threefold way, and they are classified by time reversal symmetry properties. This is something that I will possibly cover in the next couple of lectures. Okay, now so much so for the broad picture and my definition of matrix model. Let us now start making things concrete. So as I was just saying, you can't really work with any random matrix without any particular ensemble choice, and it is already known that there can be only three ensemble choice. So let us look at some particular ensemble choice, and in physics, as it will turn out, one of the nicest and probably the most relevant happens to be the Hermitian, the Gaussian unitary ensemble, which is made up of Hermitian matrices. So I start first with some finite n matrices. So all the matrices are Hermitian matrices. They are n cross n. And this is the Hermiticity condition. So M dagger is equal to M. So to reiterate once more, my partition function is Z. That's my path integral. My S of M. So I have changed it slightly, but it's not going to matter too much. I mean, I think in my earlier slide, I had GP by GS. Now my couplings have simply been rescaled. So now my action is trace M square. It has M cube, M4, and all the way up to infinity. Now, the things to notice is the independent quantities that we are integrating within our path integral are the diagonal entries, which MII. Then you have a real part and an imaginary part with I less than J. Of course, because of hermiticity, you don't really need to consider I greater than J because there is a symmetry within your matrix. The most interesting part within this expression of Z is actually the measure factor. And it will play a very, very major role in subsequent lectures also. Explicitly written out. So since we just divided all our elements into three parts, so you can have diagonal entries, which are inherently real because of hermiticity condition. You integrate out n of those. Then the non-diagonal elements you divide into two parts, real part and imaginary part. and you separately put measures on each of them. So that's how you are defining the measure. Now, hermiticity of M always will ensure, because my M is Hermitian, of course my eigenvalues are real, and because now I'm working with trace M square, so the thing that appears in power, if I diagonalize the matrix, it's something like minus lambda 1 square minus lambda 2 square, where lambdas are the eigenvalues. So of course it's always positive, it's a square, and it's always real, so things are always convergent. So what I have at the end of the day within this slide is some very nice looking, well-defined quantities. Now we will start doing field theory with them. Now, like in usual QFT, our main object of interest, even here, are correlation functions. Now, instead of working with the full-fledged theory, what we will do is we will now make our life even more simpler. We will specifically focus on Gaussian matrix model, which means all these higher coefficients that you see, G3, G4, and so on and so forth, the higher powers of M that you see in the action, I'm going to completely neglect. So my action is just 1 by 2 GS trace M square. That's it. Now, I need to define correlation function. So correlation function of any functional which contains M is defined here. It's I mean, so the angle bracket G basically stands for Gaussian, and all I'm saying is that once you have an object like the expectation value in a Gaussian ensemble, all you have to do is multiply that function with this kernel e to the power minus 1 by 2 gs trace m square, which is what you saw in the partition function, and integrate over all possible configurations of M. This is exactly what you do in usual field theory also. Now, of course, there is a choice of what is a good choice of M. And as we will see that gauge invariant objects like trace and so on and so forth are indeed good choices of such objects. And you can see why, what I mean by gauge invariant now. So the action that you see, so all the terms in the action, they involve a trace. So now if I do a transformation, M going to U dagger, M, U, of course, because of cyclicity of trace, these terms are going to be completely invariant. So there is a global symmetry in my problem where M is transformed with a similarity transform by a unitary matrix, and such transformations keep my action invariant. However, so in fact, this is what I mean by gauge invariance. The action SM is invariant under the transformations due to cyclicity, but all tracial operators like trace m to the power k, they are also equally gauge invariant. So these are what you would call nice operators. If this U specifically now belongs to unitary matrix, then what you can do is you can exploit this symmetry, and with such unitary, of course, given a Hermitian matrix, you can always find a unitary matrix which will diagonalize it. It's a theorem. Now, what is noteworthy here is if you do such a transformation though, the measure factor, because you're doing a transformation, a Jacobian is going to pop up. Now that Jacobian is going to affect your measure. However, if you restrict to something called the singlet sector, which is again something that I'm going to discuss in the subsequent discussion, this will give the path integrals a concrete meaning, and it will be in some sense more tractable. Of course, there has been some recent work in the non-singlet sector also, but things will become clear as I describe more. For the time being, there is no need to worry so much about the gauge invariance issue. The central upshot as of now is this is how we define our expectation value of objects. And right now I am working with the most simplistic model you can think of, which is simply Gaussian, trace m square. That's my Lagrangian. Okay. Now,
So I have a
yes,
question.
yes, sure.
So when for Hermitian matrix, you have some unitary transformation which can diagonalize the matrix. So
Yes.
provided that information, do we need the in the measure factor? Do we still need this d of real mij and d of imaginary mij?
Yes, you will still need that. You see, you have diagonalized it, but I mean, you have started with this original object, right? This DM.
Yes.
Now, when you apply U dagger MU or U inverse, U is unitary, so U dagger is the same as U inverse. If you apply u dagger mu, of course, this part, this d real of mij and d imaginary of mij, is also going to be affected. And they precisely are what is known, they form what is known as the angular sector. So this thing that I was talking about, singlet sector are things that are along the diagonal. This will become clear probably in the next discussion session,
Sure.
where I will explicitly show. But the point is very simple. I originally had a variable m where I had non-diagonal elements. Now I am doing a transformation where the non-diagonal elements are going away, but they will affect the Jacobian.
So Debangshu, the major change is non-trivial, right?
The measure will change non-trivially, but
It will change.
what? Huh?
Yes. So in that sense, is it related to some? Means, can you interpret it as some anomalies or something?
It will give rise to anomalies, but analyzing. So what people do is that extra factor that you see, people look at only those states. So what is going to happen is the following. This object u that you see, m going to u inverse mu, you are going to write the unitary matrix as e to the power I times a Hermitian matrix. Let me call that matrix L. What you will see is, in this measure factor, what appears after doing the transformation are things that are dependent on L. This is what you can interpret it as some kind of angular momenta. Again, this will become explicit when I show the explicit calculation. What people do is they then say that, look, I am only going to look at those states which are invariant under rotation. The moment you say that, you are acting your Hamiltonian, etc., all of these things only on those states which are dependent on the MII components. And you simply quotient out whatever is there in your non-diagonal elements. So that's why it does not affect. And this is why people mostly prefer working with gauged matrix model. So this is what is meant by gauging out the matrix model. So they literally gauge out, and then they say that we are only going to focus on the singlet sector. Singlet sector precisely means those sector or those states which are invariant under rotations by a unitary. That's what it means. But yes, there will be anomalies, and so in order to derive the explicit form, what I need to give to you is a metric, that is a metric on the space of Hermitian matrices, and that I have not defined yet. So that I will on Tuesday I will discuss that. Yeah, not today. Yeah. Okay. Are there any more questions? Okay. So before delving into this propagator, let us just do a quick warm-up of a much more simpler object, namely the Gaussian vector model. So each field has a single index. So now we will take a very, very operational point of view of what we want to do. Things which has two index will be matrices, things which has one index will be a vector. We are not going into any kind of deep mathematical complication of what these things are, what they map from which space to which space, and so on and so forth. So a generic endpoint correlation function of n such objects, n such size, is defined like this. So you have this e to the power, the action. And if this object A that you see that appears in the measure, in the integrand of each of these integrals, if this is a positive definite metric, the path integral will be convergent and it will be well defined. If n is odd, if there are odd many size, we all know that the Gaussian integral will vanish. That's simply because the integrand becomes an odd function, so it has to be even. If n is equal to 2, that is, you have only two such size and you're trying to find the correlation between them, you can do this integral explicitly and it will turn out to be the inverse of the ijth element of A. A generic 2-point correlation function, generic 2m point, because only evens survive. So that's why I have taken n to be 2m. That also one can define. And this is what will follow Wick's theorem. So a generic 2m correlation function will be sum over pairwise products. So a particular example is this 4-point function that I have written here. I have ABCD, and all I have done is I have taken things pairwise. I have taken their product and summed them. That's usual Wick's theorem. And this is something which is generally true for any theory with a leading Gaussian kernel. Now, what would we like to do? We would like to adapt this in a very brute force way in the context of Hermitian matrix model. So for us, our correlation function. So what I want to calculate is an object like Mij MKL, where Mij and MKL are simply two entries of my matrix. I want to calculate the propagator between them. And so this is what was my F. This is the F that I was talking about. And this thing is normalized. So this 1 by ZG. So G I am simply putting just to remind you of the fact that I am working in a strictly Gaussian ensemble. All these higher m cube, m to the power 4 terms that you saw, they are not there. So this is how we define it. Now, we already have a well-defined expression for the measure, dm, which I have defined. The diagonals, real and the imaginary part, we know form the 3 independent species of variables that we have to integrate over. Just for the sake of convenience and for simplicity of writing, what we do is because writing RE, IM, these are very cumbersome. So you just relabel MII as XA. A runs from 1 to 2n. Because MI has no repeated index, it's simply easier to just label with one single index A. The real part you call Yij, the imaginary part you call Zij. And notice that because of the fact that you are now working with a Hermitian ensemble, you don't need to consider the I greater than J sector, because by Hermiticity it's the same. You also have an expression for trace m square. And if you write trace m square, divide it into terms of real and imaginary, you get basically this expression. Notice the factor of 2 in front of real Mij square and imaginary Mij square. This again is the consequence of Hermiticity, because you have the same thing appearing in 2 elements of the non-diagonal components, Ij and Ji basically. What you can do now is just take this expression, and all you have is a n-dimensional Gaussian. That's it. A multi-dimensional Gaussian. And what you can do is now you can deal case by case. Okay, when I is equal to J, K is equal to L, what is going to happen? When I is equal to K, J is equal to L, so on and so forth. It will be non-zero only when I is equal to L and J is equal to K. Now, of course, such a process is extremely cumbersome, and dealing with this case by case is indeed not really a good way to do it. There is indeed a better way, which is again motivated by quantum field theory. And that is so this is way one. Method one is absolutely fine. You will get your answer. But I have not explicitly given you the answer yet, precisely because I also find it a bit cumbersome. Now we will talk about the standard but very interesting QFT trick that people employ. Actually, it will be good if I can use my cursor now. I might have to go out of full screen. Is that fine? Hello?
Yes.
Actually, if I make it full screen, I can't use my cursor. That's the problem.
You can switch on from the keynote. Go to keynote and then preferences.
Okay.
Keynote and settings. Settings maybe. And then slideshow. Maybe slideshow, yes. And then show pointer when using the mouse or trackpad. Yeah, the second one. Let's see if it works.
Thank you. Thank you, Ashutosh.
No problem.
Excellent. Perfect. Thank you. So now let us talk about this other QFT trick that we do. So this is just a warm-up. Recall how we do it in usual QFT. Suppose you have given me an action. What I'm going to do is I'm going to add to it this kind of a term, j times phi. So I had this original action. I'm going to add a j phi, basically couple the phi to a source. J is called a source, and define this deformed or source dependent path integral. Now z is a functional of j. It depends on j. J is not integrated over, only phi is. Then what you do is you take two functional derivatives of this object, this z of j, with respect to the field phi. And then you finally tune down and dial down your source to 0. What you will end up is exactly this. In fact, not just that. I mean, I have not written out things completely clearly. What you actually are getting is the connected correlator, time-ordered connected correlator. I have not written the subscript and the fact that these are connected and time-ordered. But yeah, more or less, this is what you usually do. We would like to exactly replicate this trick in the context of Hermitian matrix model. How do we do that? We already had this Gaussian piece. This was my analog of S of phi. You add to it this Hermitian source matrix, J dagger. So you add this kind of a piece trace Jm, and now derivative with respect to matrix entries are defined like this. And this is where things are going to get interesting. So matrices come with indices, right? And now when I take derivative with respect to these matrices, these index are going to do something very funny. These are going to make things complicated, but they are going to make things extremely interesting. And that is what I want to focus on. And it's very crucial that the matrix indices behave like this. So this is how you define the derivative of one matrix entry with respect to another. So you have AB, you have ij here. Simply when A is equal to I and j is equal to b, you are going to get things that are non-zero. Otherwise, whatever happens, it's always 0, which kind of makes sense. Fine. But if you naively apply this onto this object, so when I take a derivative with respect to j of the right hand side, this is going to act only on this piece, this trace jm, and this is precisely what that is. This is trace jm. But something very interesting happens when you act this. Because of the way this delta function comes out, the index structure gets swapped. That is, if I take a derivative with respect to jij, on the right hand side, I will end up getting mji. And this is extremely crucial because this, sorry, is there a question? So if there is a index swap, this also affects this computation, the derivative of the functional z. And finally, it also affects the second derivative. So the central point is, if I want something with this index structure where ij and kl is going to appear, I have to take derivatives with respect to exactly the opposite order, ji and lk, then set j to 0. So this is the thing that we need to compute. Now, once you have added this source matrix current, the source, it's not particularly difficult to sort of diagonalize the resulting thing. And what you have to do is you have to do this kind of a transformation. By the way, this transformation also has a non-triviality if you look at the index structure. This is mij, this is defined in terms of this new m prime ij, and this is jji. In other words, the transformation is m is equal to m prime plus j transpose. When you take a transpose, the indices get swapped. That's what basically this means in a matrix language. Once you perform this transformation, this gives you a new transformed action, which has the original Gaussian part in like before, except the fact that now m is replaced with m prime. But now you also have a Gaussian piece in j square. So finally, this functional which is dependent on your source is nothing but your original Gaussian times this j square Gaussian. Now again, all you have to do is simply use the derivative rule that I have defined, and this results in this extremely crucial relation. And the index structure is very important for everything that follows, like the entirety, like the field of matrix model uh, has crucial implications simply because the matrix, the index structure is this. So to reiterate again what we just saw, ijkl, the propagator, will be such that I is going to talk to L. That's what this delta function does. And J is going to talk to K. Now we start doing diagram with it. So that's what we do in quantum field theory. Once we have figured out how the propagators behave, we start drawing Feynman diagrams. We are going to do something similar here also. So once we have figured out, so of course we have not figured out all the Feynman rules of our theory. In fact, all we have done till now is we have simply got to something called the propagator, which is just the 2-point correlation function of two matrix entries. Let's see how far we can push this. So again, recall that this was what our structure was. G again means that I am simply in the Gaussian theory. But because of this kind of an index structure, something very natural emerges. You can represent these propagators actually in what is known as a double line notation. So in some pieces in literature, you are also going to be seeing that they are referred to as ribbon graphs or fat graphs. So instead of a single line, which you do typically for a Feynman diagram in quantum field theory, here you will represent a propagator with two lines. And there is a deeper mathematical reasoning behind it. It's because it's a representation theory related reason. It's because any unitary representation actually of M can be decomposed into a fundamental times an anti-fundamental representation, and one of the first index is supposed to signify the fundamental, and the second one is supposed to be the anti-fundamental. So in this sense, it has to be a double line actually. But even without that, you can totally understand why you have I to L and J to K. It's precisely because of this particular index structure. Higher point vertices also has some double line representations. And yes.
What about the arrows?
So arrows signify from which. So what are these indices? These indices are, if you try to think in terms of gauge theory. In fact, we will talk about Yang, Mills, and Chen-Simons in subsequent discussion sessions. These arrows represent the flow of color. So that's what this means. IL, yeah, I mean, it always goes left side in the first delta function and right side in the second delta function. That's what it means. The arrows represent the direction of flow of your color. That's it. Yeah.
Basically, color neutral.
They are all the propagators are color neutral. So I mean, I could have, so this is a matter of, by the way, if you are asking, the directionality in itself is a matter of convention.
Yes.
If I could have, I mean, I could have as well swapped the upper one from right to left instead of going left to right. But in which case I had to naturally change the orientation of the one below. So you can follow any convention, but you have to stick to one. It always has to be color neutral, because color has to be conserved. That's the central point. Yeah. Okay. Now let us look at higher point vertices. They also have this typical double line representation. This is a typical cubic vertex. This is a quartic vertex. So let us actually calculate some correlation function. So what I will show you an explicit calculation of is the correlation function of this object, trace m to the power 4. I apologize about this. I have used here ABCD. I should have used here IJKL because the diagram has IJKL. But I mean, I think it's obvious. A is I, B is J, C is K, and T is L. Yeah. And yeah, you can see here how, yeah, this is the, yeah. So as I was saying, our main goal is to compute this particular object, trace m to the power 4. So by the way, just to reiterate once more, why are we interested in things like trace and stuff? It's because of this reason that if I do a simple global transformation with a unitary matrix, these objects remain invariant. So this is some kind of zero-dimensional version of your gauge invariance that you see in gauge theory. So as discussed, since we are doing a Gaussian theory, if we want to calculate this, we will use Wick's theorem. So this is the object we want to calculate. We use our standard Wick's theorem and we divide things pairwise. I have Mij, Mjk, Kl, Li, and of course, each and every line here is crucial because I have to take care. I think one thing is quite clear to you now, that the index structure is very crucial in all of this analysis. Okay, so this is what we get from Wick's theorem. Note the first term and the third term. So remember, there is a sum. Okay, I have messed up a little bit. There is a sum over IJKL which is absent here, but yeah, there is a sum. I have explicitly written here only in this part, and I somehow missed it here. But there is a sum in front. So look at the first piece here, IJJK. So there is a J that is summed over, and if you simply relabel things, so MLI can be put here, MIJ can be swapped here. So I is sort of a repeated index, which, because it's a dummy index, I can change it to J. And similarly, IK can also here be replaced, can be swapped with JL. And the same can be done with this piece, KL, Li, and JK, KL. In fact, the fact that this object is same as this object is kind of more explicit. So the first term is effectively same as the third term, which basically gives the first term a factor of 2. So what we see immediately is there are two distinct patterns of contraction when we apply Wick's theorem to trace m to the power 4. Now, recall, this is what we just derived as a propagator. The first talks to the fourth, the second talks to the third. So I write down Mij, Mjk. The first talks to the 4, I have a delta Ik. The second talks to the third, I have a delta Jj. A similar analysis for each of these will give me this bunch of delta function, and you can check each of these delta functions. So I have Ki here, I have Ll here. Similarly, I have Il here, I have Jk here, I have Ji here, and I have Kl here. Once you sum up these delta functions, and of course these computations are very simple, you immediately see that in the first term, I have Ik and Ki. When you sum over K, you end up with delta II. There was already a delta Jj and delta Ll present. And here I have IL, LK, KJ, Ji. So there is a cyclic combination that is going on. And finally, you end up with simply, once you perform the J, K, and L sum, you simply end up getting a delta I. Now, I runs over. So these were color indices. So they ran over n many indices. Once you perform all the sum, so delta I gives you a contribution of n, Jj gives you n, Ll gives you n. So you have n cube, and here you have n. The moment you see this, you start seeing that there is potentially some kind of structure that is already present here. What you should note is, always keep at the back of your mind that we have to take the large n limit. So at some point, we are going to make things large, and you immediately see the first term, the term that goes as n cube, seems to be hugely dominant compared to the second term, which has the same power of gs, but has only linear power in n. So it seems that certain terms will be dominant over others. Let's try to understand this further. Let us do some more diagrammatics. The natural question is, we contracted certain things here. Is there a very natural diagrammatic way to do it? Indeed, there is. So we had this 4-point vertex. Whenever you see a delta function, I'm going to connect those two legs. The first diagram, if you recall, came from contracting this object, Ik, Jj, Ki, Ll. And that is exactly what I have written out here. So let's see what is happening here. When I see the first one, I is connected to K, which essentially means, and so this is why the arrowheads are very important. So Obinabda was asking about the arrowheads. So you have to be consistent. So this is where it's very crucial. So K is connected to I, J is connected to J. So I'm going to simply take this two ends of J and complete this loop. Similarly, L is connected to L. So I'm going to complete the L loop. And finally, you get a figure like 8. This diagram is special. It's called a planar diagram. You can simply take this diagram and put it on a piece of paper. In the second diagram, the contraction was like this: IL, JK, JI, and KL. Again, if you stare at this diagram for a while, you are going to see that all the contractions are done. I has been connected to L, J has been connected to K, then another point of J has been connected to I, and another K has been connected to L. But something very non-trivial has happened in the second diagram. You see that the object connecting the left and right branches kind of passes over like a bridge. And there is no possible way I can take this diagram and put it on a piece of paper. Something will always stick out of it. This is precisely what is meant by non-planar diagrams, things that you cannot put on a piece of paper. What you can do is, so this is something that you can put on a sphere. What you can do is you can take this diagram and put it on something called a higher genus surface, that is a torus. We will come to that. Now, there are a bunch of things that we actually learned while doing this algebraic computation and trying to connect it with a concrete diagrammatics. So physically, one can think of the indices, as I was saying, as color indices, and which one encounters in QCD, and a simple vacuum diagram. So it's simply going to have two loops, and we just saw. So whenever you are going to get a loop effectively means, so if you see here, when we close this because we got a delta function here, delta JJ, and we close this. We got a delta function in LL, we close this. So the moment you get a closed loop, it means that there is a sum over delta function that you are doing. And we saw that the sum over delta function gives you n because I runs from 1 to n. So every loop gives you a factor of n. And a simple bubble diagram like this means simply two loops running around, and this has an amplitude of n square. Now, the answer we obtained algebraically could also have been obtained by doing simple diagrammatics. Instead of going through explicit calculation of the delta function, I could have drawn the diagrams and just counted propagators. So in this picture, you see there are two propagators, this 8-like figure. The propagator I'm going to call E, the vertex I'm going to call V, and the color loops I'm going to call F. There is a reason why I'm calling the propagator E and the color loop F. It will become clear subsequently. So for this particular diagram, I have two propagators, 1, 2. That's why for this particular diagram, it's GS square. The vertex goes as 1 by GS, and the color loops goes as n cube. And in fact, the scaling of n cube is precisely what we recovered when we perform this algebraic computation without drawing any diagram. For the non-planar diagram, by the way, also you will recover a factor of n, because you'll see that if you keep following the path, you are going to see that this is actually nothing but a single loop. You can actually traverse the edge of this diagram like this dotted red line along with the solid blue line without lifting your pen. Now, I showed you a couple of examples of quartic diagram. You can do a similar game and play around with many more quartic vertices. You can play around with cubic vertices also. So to just give you a quick snapshot of some cubic vertex, if you look at this picture, this diagram has 3 propagators: propagator 1, propagator 2, propagator 3. So that gives you a factor of GS cube. So by the way this counting works, how do I know that propagator has GS to the power something? So whenever you look at any theory like this, The inverse of the kinetic piece is the propagator. And the object appearing in front of the higher point vertex is the vertex factor. And that's precisely what we have done. So the inverse of the propagator, I mean, 1 by gs was the object in front of the kinetic piece. So the propagator is gs. And the vertex factor was also 1 by gs. So that's why you have a minus sign here. So in case of this diagram, which has two vertex, once you compute everything, you get this factor gs times n cube, which I have written here like gsn times n square. This is a non-planar diagram for a cubic vertex where this n square factor is actually absent. You can in fact again trace this blue line and you see that without ever leaving the particular surface, you can complete all the loops. So that's why this n is simply 1. And the number of vertices and propagator are same as this diagram. So you're always going to get a factor of gs. This is a much more complicated diagram. It's a planar diagram which has 9 vertices, but ultimately, if you follow the same prescription, you are going to get exactly this answer. Now, in the 1970s, Thuft was studying QCD, simple models of QCD. And he studied hundreds and hundreds of this diagram, and this is where the genius of Thuft comes. He found a pattern, and the pattern is the following. You take a planar diagram, you can always write it as this factor of gs times n times a n square. You take a non-planar diagram at same order. So this is a 2-vertex diagram. This is also a 2-vertex diagram. Always the non-planar diagram will be suppressed by a factor of n square. It will be missing this factor at least. I mean, there can be higher, it can be off by a factor of 4 and stuff also. But of course, it will always, any non-planar diagram will be off by at least a factor of 2. Which essentially means if you take the large n limit, the things that are going to be most dominant in your partition function are planar diagrams. And this very apparently harmless looking statement is at the core of quite a pretty dramatic revolution which brought quantum gravity. In fact, what you are looking at, this very harmless looking thing, is the first avatar in a sense of ADA-CFT.
Sorry, just an observation.
Yeah.
That if I take, say, your first two diagrams in this slide, so like if I just take the planar diagram, and if I'm allowed to kind of cut and paste, then if I try to do that and make the same,
you cannot cut and paste.
No, I cannot. What I'm saying, that if I do that and make it a non-planar diagram, so what is happening that, so if I follow the number of loop logic, so what I'm doing something like, say, like a Mobius strip.
Yeah. What you are doing is, so
if I do that, I actually decrease the number of loops.
Yes.
So that means that if the planar diagram has some n to the power some alpha, so if I cut and paste and make it like a Mobius strip, like I increase the embedded dimensionality, then I'm decreasing the number of loops. So obviously the power of n will go down.
Yes.
So if you do that, so means that planar diagram will always have a higher power of n.
Yes. That is precisely the point.
Yes.
That is exactly the point. So in fact, you're absolutely right. If you see, in order to get the second diagram from the first one, you have to chop off the middle propagator, give it a twist and rejoin it. That will give you actually this diagram.
But that will basically join two loops into one.
Yes. And that you are not allowed to do.
Yeah, that I'm not allowed.
You cannot, yeah. Because like you are literally changing you can only identify topologically non-distinct diagram, because here you are literally changing, you're changing the genus actually. So
yeah, but that also says that planar diagrams will have higher powers of n.
Yes, that is precisely the reason why planar diagrams has higher powers. So now What Thooft did was he went one step further. He defined something which is popular now as the Thooft limit, where n is large, gs is small, such that their product, which is called lambda, this is fixed. This object lambda has a name, it's called the Thooft coupling. Now, what you just saw, these planar diagrams, you can think if you put these planar diagrams on a sheet of paper, you can imagine that this is breaking up this sheet of paper into a bunch of small, small sections. This process, this geometric process has a name, it's called tessellation. And the moment you have something like this, it is very natural to identify the color loop as faces, the propagators as edges, and the interaction as vertices on a typical Riemann surface. Now, instead of working with GS, so I was kind of counting here power things in terms of GS and N. So GS is nothing but lambda by N. I take this generic formula. So if I take a typical diagram with V vertex, E edges, F faces, planar diagram, and if I write down the amplitude, this is what it is going to be. Lambda by N to the power edge, N by lambda to the power vertex, and number of faces. And once you simplify, you will get a power of n which should shock you. Because what you are looking at is vertex minus edges plus faces, which is nothing but the Euler characteristic of a Riemann surface, which is a topological invariant, which is also related to the genus of a surface. G is the genus. So genus, basically, to put it in a very layman term, it's sort of like the number of handles that you have on a 2D surface. So you have something like a donut, that's a genus 1 surface. You have something like a pretzel, that would be a genus 3 surface. So it's very loosely speaking the number of handles that you have. And now, because this is a topological invariant, and now each and every term is n to the power such 2 minus 2g times some function of lambda, some function of the Thooft coupling. By the way, all these has followed from heuristic calculations. Till now, we have not computed the exact amplitude for any diagram. What you can say is that once you sum up everything, this is how the partition function will look like. It will look like n to the power 2 minus 2g times some complicated function of the Thooft coupling. And this is one more place where you see why planar diagrams were the ones that were contributing the most. Because planar diagrams does not have any handles, it does not have any holes. So for planar diagrams, G is 0, which is what makes, so because this power is most dominant when G is 0. For any other G, it's always going to be less than that. This is precisely what is known as genus expansion, where G is the genus, and as I just explained, these are basically nothing but handles. The non-planar diagrams corresponds to surfaces with handles, and they are suppressed by factors of 1 by n square. Now, magically, it turns out this exact same formula turns up in another place in its partition function. And this is exactly the partition function of closed-oriented strings. So, in a sense, all this while, what you have been looking at is a two-dimensional string theory in disguise. That's it. Because they have the same partition function. If two theories have the same partition function, they are the same theory. So the analogy between genus expansion and perturbative strings should be one of the most strongest motivation to believe that gauge field theories and string theories are effectively nothing but two sides of the same coin. And this is precisely what is considered one of the biggest motivating factors of advent of ADS-CFT. Because ultimately, once you look at low energy limits of string theory, that is nothing but gravity. So now you can go ahead and say, okay, maybe there is some limit in which I have a gauge theory and its dual will presumably be a theory of gravity. It might not be an exact map, but there has to be some point within your parameter space or your coupling space where you can possibly do this map. All of these finally culminated in this extremely seminal paper, which came all the way back in 93 by David Gross and Brian Washington Taylor. And the little title is Two-Dimensional QCD is String Theory. So to summarize everything, what we did was we started by defining a very simple field theory, extremely simple field theory in zero dimension, where the dynamics were governed by Hermitian matrices, whose entries were randomly drawn from a Gaussian distribution. And we carefully defined its propagator. And throughout, I think by now you are absolutely convinced that the index structure is the thing which made it work. And it's very crucial that all the computations are done with the correct indices. And we worked out a sample expectation value for trace m to the power 4. We now know how to compute these. And in the large n limit, we explored this diagrammatics in full glory, and which eventually led us to the 'th limit, where we found this very nice pattern. And eventually we expressed, and we saw that planar diagrams are the ones which contribute the most. And once you write down the full partition function, you can write it as a genus expansion, which matches exactly with that of string theory, whose low energy limits happens to be gravity. So even with a very, very simple setup, we have managed to get a huge mileage into possible connection between gauge theory and gravity. And with this, I end today. I think I have already crossed my time by quite a while. But just to give you a teaser, what is going to come. So one thing is the question by Arpita and Abhinavda that about the transformation, how U affects things. And what we are going to do is, in the next discussion session, we are going to write things in eigenvalue basis. Instead of using generic MIJs and things like that, we are going to actually diagonalize M and express the path integral as an integral over its eigenvalues. We will discuss what the singlet sector is. There will be more interesting things that the measure is going to do. And that is going to bring us to some interesting object called the van der Waals determinant, which is going to play a very crucial role and make these field theories behave like a bunch of electrons. This has a name. It's called the Coulomb gas formalism, because they have this gas behaves as if like all the particles are repelling each other. It's a bunch of fermions that are trapped within a potential well. Then we are going to move on to a collective field theory description, or rather, how exactly would you do field theory with all of these? Because till now, all we did was a simple heuristic calculation, and that itself motivated us. And we actually managed to recover the genus expansion of string. How do we actually do collective field theory? Like how to get and explicitly write down a effective action, which is a sort of continuum action, like which will have a well-defined kinetic term, like the way we do usual field theory, starting from a matrix model. And of course, that will be followed up with probably, so this is something which is a very interesting topic to me, which is matrix quantum mechanics, where all the matrices that you saw, they are going to become functions of time. And once you introduce such dynamics, now it won't be a zero-dimensional theory, it will now become a 0 plus 1-dimensional theory. And yeah, which will have very direct links with what is known as Liouville field theory and C equal to 1 CFTs and so on and so forth, which I hope to get to in the next few lectures. So yes, so this is what I had to say today. So thank you. I mean, I will be happy to answer any questions.
Thank you, Debangshu, for this wonderful talk. So anyone have any question?
Yeah, I have a question, Debangshu.
Yes.
What about the case with when we have Lorentzian manifold, like we have assumed Euclidean manifold for all these discussions?
No, there is no manifold here. So what I have
the
assumed is
background.
I have not. So it's zero dimensional. Throughout, I have stayed in zero dimension. I will bring in time, and at that point, I have to bring in matrix quantum. Like you are talking about matrix quantum mechanics. When you talk about matrix quantum mechanics, okay, we are going into dangerous territory now. Once you bring in time, you have to, like, all the discussions that I will do at least will be with Euclidean time, actually.
Euclidean time, okay.
Yeah, but Euclidean and Lorentzian has vastly different behaviors.
Okay.
And also this is you can also see this even in the context of Chern-Simons theory. Um, and also there are so there is this entire field of study called resurgence, which is related to this, and it matters basically whether you have a decaying sort of an integrand or you have something oscillating, which is precisely the difference between Lorentzian and
Yes.
Euclidean, because you have,
Yeah.
for Lorentzian you will
Iota.
have a factor of I, and
Yeah.
that changes things drastically.
Okay.
So here my M does not have, so you see my S of M does not have any integral over any manifold.
Right.
So this is not yet a functional S of M. Once I make it matrix quantum mechanics, it is going to become a functional. I'm going to have integral dt here. M's are going to be functions of t, and instead of trace of M square, I'm going to write trace of M dot square. So then things will become much, much more interesting, difficult, and yeah. Yeah, but it will take some time to get there. There are other things. There.
Thank you.
And also there are some dual theories where matrix models are sort of like a dual description of higher dimensional gravity theories. So in that case, in the dual picture, you can have some notion of Lorentzian manifold and other things. So yeah.
I see.
Indeed,
Thank you.
Indeed.
So if there are no any other question, okay. Sure.
Just one small question, just a inquiry that so because you are talking about a gauge theory, so what about ghosts?
The ghost will come into the picture. Firstly, one thing is that this is not a gauge theory yet. U's are not functions of anything. Today, there was no gauge theory. These were global. Everything was global. I have not spoken anything about matrix quantum mechanics yet.
Okay.
We are still within the realm of U's are global. They are not functions of anything.
Okay.
I know this is a bit, how do I say? This is a bit misleading to call it gauge invariance. But this is like a very, I mean, I use the word gauge invariance very loosely. This is not, this is a global symmetry, just to be clear.
Yeah. That's understood. Anyhow, it is it's just a unitary transformation. So
yeah. So
okay, we'll wait for that.
Sorry.
We'll wait for that. Like, can you don't trivialize the things more?
Yes, I will. Yeah. But what my central message today is the fact that there is this very, very close connection between large and matrix model and gauge theories and gravity.
That I really appreciate. Actually, I appreciate it more because long back in a CRC main school, I attended a large and lecture by Gautam Mandal.
Oh, okay. Yes.
So I was doing this kind of diagrammatics then, but starting from this 1+1 dimension string theory.
I see. Actually, you don't need higher dimension. Like, you can actually realize all of this beautiful diagrammatics in a very simple, like Gaussian zero-dimensional model itself.
So, like when you say that it is equivalent to two-dimensional string theory, I have already seen it from the other side. So it was really helpful. Thank you.
I just have one more question,
Yes.
Debangshu. So maybe I don't know if I missed something, but is this the statement that in the large and limit the planar diagrams dominate? Is it applicable for UN matrix models as well as ON like vector models, or is it specific?
Yes. Okay. Good. It's an ensemble independent statement.
Okay.
Yeah. It's an ensemble independent statement. So
Okay.
instead of doing this, so the computations will be significantly difficult for GSE, symplectic. GOE will be tad bit easier, but this is generally true. instead of working with this, if you work with a theory if you work in GOE also, things are going to be the same.
Okay.
So also one thing I should say to everybody is I have not given references. I am going to give it on Tuesday. I will start with all the papers and books that I am using to discuss these things, and some review articles also. Yes, some review articles also.
Okay, so if there are no more questions, then I will thank Debangshu again for this beautiful talk, and we will end the session here.